My name is Henry Olson, and this is our model, the China water crisis model. And our model question is, will China have sufficient water resources to sustain population and agricultural growth? And so basically in this model, we looked at China's current water crisis, which is that China does not have enough water to sustain its population and its agriculture. And so we wanted to model this to see what sort of policies China might need to fix this problem. And my partner Cameron is going to explain a little more in depth.
All right. So currently, China is one of the nations in the world that is experiencing a water crisis. There simply are not, at the current time, there are not enough water resources to sustain population and agriculture in China, and it is predicted that this problem will get worse in the future. The water crisis would naturally have a serious impact on China's population and its food supply. And predictions would see that the amount of available water would decrease and China's population growth would stagnate because of this lack of resources.
Alright, so now we're going to take a look at our model, and we're going to show you in segments in the order that we built the model. And so we're going to start with the water segment, and Cameron is going to walk you through how that works.
So the first segment we have in our model is the water segment. Excuse me. Get this such the main components of the water segment are the total water resources stock and the freshwater available stock, which have flow structures in the water, renewable water resources, water captured, and total water use. There are also other factors that affect these, which I will talk about later. So first, the total water resources represents all the fresh water within the geographical region of China. This includes groundwater, water coming from rivers and glacial melts, and in other bodies of water. The inflow into this stock is renewable water resources, and this flow represents the water that every year is coming to China through rainfall, melting of glaciers, and rivers that flow into China and create this water stock. However, not all of the total water resources within China are able to be utilized at any given time. So a certain amount of water is captured to be available for people to use, and that is represented by the water captured flow, which goes into the freshwater available stock. And this stock is the one that represents water that is actually utilizable by people. Additional flows in our model include the polluted water outflow, which decreases the amount of total water resources as pollution increases. And both total water resource and fresh water available have outflows that represent overflow because we would assume that there is a maximum capacity of water that can be held within that region, or the maximum that can be held within reservoirs and water infrastructure. Finally, we have our wastewater stock, which is fed by the inflow total water use, which represents water use for domestic or agricultural purposes. Some of the wastewater is treated in our model through the water treatment flow, and the rest is drained out just as is drained out of the other stocks. Okay. So our next, which one? All right. Our next segment is the population segment, and Henry will explain this.
All right.
Scroll down.
Or I think this is pollution right now.
pollution.
Yeah, do you want to talk a little bit about pollution?
I didn't realize these were separate. Oh yeah, so this next segment we just brought up is some of the modifiers that affect the water segment of our model. The population stock increases the rate at which water becomes polluted as population increases, and also increases the amount of water used. The agriculture is also represented. Oops, I didn't mean to do that. There, right. Agriculture is also represented by the farmland stock, which uses a significant amount of water. So the more population and agriculture grow, the more water will be used. All right, now we go to population.
Okay, so I'm going to talk about the population and agriculture segments, which are basically add-ons to the water crisis. So in our population segment, this is the very basic segment that we built originally, and the main component is the population stock, which represents China's population. We have the births and the deaths, which are both affected by their respective rates. And this is our basic part of the model, and we later expanded on it. And what we have here is a little loop that we formed where we have the desired amount of fresh water per person, because every person needs a specific amount of water to be able to survive, and the water is also used for other things such as like laundry. And so they need a specific amount of water, and this is compared to China's total available amount of water, which comes from the freshwater available stock up here. So there's the amount of water that's available for domestic use, and the amount of water that is desired by China's entire population forms the available desired water ratio. And so as this ratio changes and there's more available water than is needed, this effect modifier goes into the actual death rate and makes the death rate decrease, because there is more water than is needed and there's almost no crisis. But when there's less water available than is needed, the effect converter makes it so that the death rate will increase, because there's less water, people aren't getting the water they need to survive. And so that will cause an increase in the death rate and an increase in the deaths. And down here, we have our agricultural segment. And this is based around the farmland stock, which represents all of China's acres of farmland in which crops are being grown. And there's two flows: the inflow, which is agricultural growth, which is over a period of time more farms being added into China's land, and then agricultural decay, which means farms decaying and deteriorating because they can't be maintained. And so this segment kind of works in a similar way, in that the fresh water available, if we go over here, the fresh water available means that there's a certain percentage of the fresh water is available for agriculture, and this percentage also goes into an available desired percentage, where there's a certain amount of water needed for farmland and the amount of fresh water available for farmland. And this ratio also affects the decay rate of farmland, just like the ratio in the population segment affects the death rate. So when there's less water available, the death rate or the decay rate is going to increase, because there's not going to be enough water to water all of the crops, and some of the farmland is going to deteriorate. However, when there's more water than is needed, the decay rate will probably decrease by a little bit, because all the crops can be watered. Also, there's a little segment here about food, because the farmland produces crops which are used for food. And so based on the population segment, this available needed food ratio is based on the total food that is needed by the population and the total food that is produced from all the farmland. And when this food ratio is low, meaning that there's less food available than is needed, then the population is going to decrease, because there are going to be more deaths because there are more starving people. But also, when this food ratio decreases, this effect converter will increase the growth rate of farmland to ensure that more crops are going to be grown to counteract the increasing death rate due to a lack of food. And so this is kind of a built-in structure to prevent too much deaths due to starvation. However, this structure will ultimately fail if there's not enough water to water the new farmland, that is trying to be put in here. So this is our basic model. We've got agricultural, population, and our water segments. And now we're going to take a look at our feedback loop. I'm going to talk about this also. So here's our feedback loop, and it's a pretty basic feedback loop, and what it is it's the freshwater and death rate feedback loop. So this is the loop that is going to be focusing on how the amount of fresh water available is going to impact the death rate and ultimately the population of China. So when the fresh water available increases, there's more fresh water. That means there's more available water for domestic use. A certain percentage of the fresh water available becomes available for specifically domestic use, and this will increase the available desired water ratio. When there's more water available, the ratio increases, which means that the death rate is going to go down because there's more water available for everybody. When there's more water available, the death rate is going to go down because there are fewer people dying from lack of water. So the deaths will go down because the death rate is going down, and this will result in a larger population. With a larger population, there's more household water use because there are more people, more families, and more uses for water. So this increases total water use and will increase the amount of fresh water available that needs to be used. This will cause a decrease in fresh water available, and so that means that when fresh water available is initially increased, it will eventually result in a decrease in fresh water available because it will cause an increase in the population, and a higher population needs more water. So this presents kind of a problem because if there's more water in the system, it really won't help anything because eventually that larger population that results from having more water is going to need to consume even more water. So this loop is counteracting. And Cameron is now going to talk about some policies that are going to help mitigate this problem.
So in our model, we tested hypothetical policy scenarios that could possibly reduce the severity of the water crisis and its effect on the population. So we considered a situation where the government took steps to reduce the amount of water pollution being created by population and other sources. And in this case, pollution is being reduced by 0%, 10%, and 20%, I believe. And so this graph shows the amount of polluted water, and if government decide the amount of water being polluted each year, and if the government decides that they're going to impose strict regulations, then they could significantly decrease the amount of water polluted. Is this? Yeah. And ultimately what it would be able to do is allow more fresh water to exist in the system that is free of pollution. And this greater fresh water would allow a little more significant growth and sustaining the regular rate of growth and standards of living for the population of China. All right. So Henry will present our conclusion.
So to wrap it up, we learned that the process of modeling is a really interesting way to look at how to solve a problem, because with the modeling process, you learn how to look at the components of a problem rather than just the problem itself. And so in this situation, we looked at the different components, the agriculture of the population and the water, and we looked at how they all affected the system. And in doing this, we were able to kind of solve the problem and see where this crisis was occurring. Was it occurring from a lack of water or from inefficient use? And so we were able to see this through the modeling process, because it's a really interesting way of looking at all the different parts. And so this modeling process can be useful in many different things, especially when trying to solve situations that are very complex. And we found in the end that China will not have enough water to sustain its population if it continues to use its water the way it does now. The crisis is kind of based on inefficient water use and unequal distribution of water between China's different water basins. And so something needs to be done about the pollution and the distribution of water in order to slow down this crisis. Otherwise, we could potentially see China's population and agriculture take a huge hit. And this is especially a problem for China, who has been traditionally self-sufficient in food production. And so if they don't have enough water to sustain their farmland, they may see their food production shifting. They might have to start importing more food in order to support their population. So we found that this crisis is very real and that the government might have to take significant steps in order to combat it.